So our next step is to do astronomical distance measures. So this is where we start getting into some very, very big numbers, and we need things larger than a meter stick to just depict and represent those distances to nearby solar system objects and beyond, you know, within our galaxy and to other galaxies. So let's start. So for, you know, relatively close objects, and I'll specify solar system objects, and by this we mean like the moon. You know, sometimes we might talk about meteors or satellites like the International Space Station that's in Earth orbit going around the Earth. So, and even, you know, you can even use kilometers to represent distances to the close planets like Venus or Mars. So relatively close solar system objects such as the moon. I'll say other satellites like artificial satellites. The moon is a natural satellite. Satellites, ISS, the International Space Station, sometimes close rocks, like asteroids, if they come close in the orbit, ... We use kilometers. Okay. And there's the prefix spelled out. Okay. So for larger solar system distances, now more like the distance to the sun or the distance to the planets further away, the distance to the outer realms of the solar system, the distance to space probes that are further out, we use for distances around the solar system in general, further out. So for example, the planets, outer the belt, asteroid belt, the Kuiper belt, let's say Kuiper belt, distant probes, etc. We use AU. Okay? And AU, what does AU stand for? That's called an astronomical unit. And how do we define an astronomical unit in astronomy? An astronomical unit is the average Earth-Sun distance. There's some times where the Earth orbits around the sun and it's closer to the sun, and that's called perihelion. And there's some times where the Earth orbits and it's further away from the sun, and that's aphelion. So what we do is we say the average distance, where 1 AU is equal to, or is defined as the average, very important to know that, okay, is defined as the average Earth-Sun distance. And there is a number for that in kilometers that we can relate to. So remember, we use kilometers for, like, you know, driving distances, distances across a country, distances between cities, etc. And 1 AU is our conversion we can use to kilometers. So 1 AU is defined as the average Earth-Sun distance, and 1 AU is equal to 1.496 times 10 to the 11 meters. So that's quite a distance there. We could do some conversion with that. So 1 AU is pretty far away. And what we want to do is think about how we could do some conversions using AU. Okay. Now, if it's 1.496 times 10 to 11 meters, I mentioned kilometers is our typical conversion. This would be the same thing as 1.496 times meters are smaller than kilometers. So if I'm going to make my unit larger, I need to make my power 10 smaller. So going from meters to kilometers is 3 powers of 10. So I'm going to reduce my exponent by 3 powers of 10. That becomes 11 minus 3, and that's to the power 8. Okay, so this is a very, very important conversion factor we want to use if we want to convert between kilometers and AU distances. So let's go ahead and do an example. So it's a large, large distance. So AU conversion example. Okay. So, we could say, what's the average distance between the Earth and the Sun? Well, we can memorize this number and we say, oh, it's just 1.496 times 10 to the 8 kilometers. Okay, now let's put in perspective, how many more of those would we need to reach Saturn? Okay, or how many more of those would we need to reach, Pluto when it's at its furthest orbit, which is a dwarf planet? Or how much more of those would we need to reach one of the Voyager probes, the furthest man-made objects in the solar system? Well, let's start with Saturn. Okay, so if Saturn is approximately 9 AU from Earth, and we're just going to say its average distance because this fluctuates a lot. Sometimes it could get all the way up to 12 and 13 AU depending upon the Saturn's orbit around the Sun and Earth's orbit around the Sun. So if Saturn is approximately 9 AU from Earth, how far away is it in km or kilometers? Okay. So for a problem like this, you would look up the AU on a table, the AU conversion factor, or it would be given to you on a test, and you'd say, okay, what I need to do is start with saying 9 AU will equal my conversion factor between AU and kilometers, or maybe I only have AU in meters and then I have to take one extra step to make it into kilometers. So I need my conversion factor, and then I want my answer to equal so many kilometers. Okay? So in this case, directly I'd want to get rid of my AU. So I say 1 AU is equivalent to, I'm going to go directly to kilometers, 1.496 times 10 to the 8. Okay. And this will get rid of my, I need to multiply that. This will get rid of my AU values and produce the answer I desire in kilometers. Okay, so what I need to do right now is multiply 9 times this large value. So I'm going to go on here and I'm going to say 1.496. For my power of 10, my scientific notation here. Okay, so in this calculator I actually have a button that says times 10 to the power of. So 1.496 times 10 to the power of 8. And then I'm going to multiply by 9. I could do multiplication anywhere. And I get this value, a very, very large number. And this gives it to me with all the zeros. 1, 3, 4, 6, 4, 0, 0, 0, 0, 0. So you can see the utility, making sure I have enough zero. The utility in scientific notation, because it's easy to lose when these numbers get big. It's easy to lose some of these numbers. So I'm going to express this as 1.3464 times 10 to the power of, let's see, 369 times 10 to the power of 9 kilometers. And that's a better way of representing that number. But that's how we would do the conversion. So that's on average how many kilometers away Saturn is from Earth. Make sure you interpret this correctly. You will go online and you might say, oh, what's the average distance of Saturn? And sometimes they'll give you the average distance from the sun. Okay, so what this means is that Saturn is on average 9 Earth-Sun distances. So that's pretty far out. Okay, so we expect colder environments out there, and that really had a lot to do with the evolution of the planets, because they're so much more further out. The evolution of the outer planets are much different than the evolution of the inner planets because of how far away from the sun they are. Okay. So let's go on to our next distance measures in astronomy. I'm going to step it up. Okay, so far we have number 1, we have kilometers. Okay. Number 2, we have AU. Now going even to a greater distance, we get into the light years. This is when we start leaving the solar system and going beyond the solar system. Even like the little cloud, the Oort cloud around our solar system, we can start expressing in terms of light years. We're looking at 1 to 2 light years. That's still sort of unknown territory. The boundaries of our solar system are unknown, and we hope to know more. And another curious thing too is you can look at Voyager. Voyager is about the furthest spacecraft that's leaving the solar system, and that's over 150 AU away. Yeah, 150. Voyager 1 is approximately 152 AU away. So that's really far away. Outside the solar system, for example, to the nearest stars, to the nearest galaxies, beyond, so I really should say even further than that, because we use that even in our numbers for what's called the observable universe, all that we could see, as far as we could see from the light that surrounds us. We talk about something, we measure light year. And the symbol for light year is LA. H, or sometimes they'll say LY, excuse me, or LYR. Okay, so what in the world is a light year? And this is where it gets mind-boggling. So now we're diverting away from what the standard, what a meter looks like. Now we're going to be talking about distance in terms of the speed of light and the time involved. Okay, so the light year is a little more complex. So if I could turn on my laser and measure how many meter sticks that light will cover over a period of time in a year, right, traveling at the speed of light, I would have a light year stick. Now that's mind-boggling because light travels at 3 times 10 to the power 8 meters every second. So you add up all those seconds for a year. So you have 3 times 10 to the 8 meters, plus another 3 times 10 to the 8 meters, another second, times plus another 3 times 10 to the 8 meters. So you add all those seconds up until a year, and you would have the meter distance covered in a light year. That's huge. So let's take a look at this a little more formally. So this is, we could say, the distance so we could say the light year, which is the distance now. It's a measure of distance, not time. It is related to time, so we'll talk about that. It's a distance that light covers or transverses. I'm going to use the term covers because I think that relates it or communicates it well. The light covers in a year traveling at its speed, which is the speed of light c in a vacuum. So I do have to add in one little factor, like you could slow light down if you shine light through glass. It's not going to be the same as the speed of light as it travels through space, which is nearly a vacuum. Okay, so if we take out the interaction with any other atoms in the medium, light will travel at 3 times 10 to the 8 meters every second. So that many meters every second. So this is that distance covered by light when it travels for a full year. So very, very important to wrap your mind around that. Okay, and I will circle this. And what is that value? We would say where 1 light year, we could use this conversion a lot, is equal to 9.46 times 10 to the, this is in meters, and I don't have these numbers memorized. I actually like to derive them if I need to. I do have this number memorized, and I can figure out this number based on that number. Okay, so this is also equal to 9.46 times 10 to the, if I change it to kilometers, I'm going to make this smaller by 3 units, 12 kilometers. Okay, so you use which one you need to. Okay, so let's take a look at some of these distances. Now the nearest star, Proxima Centauri, it's a triple star system, but the one that's closest to it is about 4.2 light years away. So to get some understanding on how that light year measure works, we have to think about this idea of sending a light signal. So that includes radio or laser light, or sending microwaves from that placement in the galaxy or in the universe. If we send it from that object 4.2 light years away, in this case Proxima Centauri, let's say we send a laser beam off the surface, it would take 4.2 years for that light to reach us, traveling at the speed of light, and assuming again it's a vacuum. So what happens is that number really reflects a lot. What we're doing is we're looking at the history of that light. So we're looking at the light of distance past, and this is why we say looking at the night sky is like a time capsule, a time machine. What you're doing is you're looking at history, because all the starlight is light that was emitted a long time ago. So some other numbers, so some examples of light year distance would be like Proxima Centauri, the closest star to us, besides our own sun, of course, which is approximately 4.2 light years away. That's my L. Sometimes I do a squiggly L, sometimes a straight L. But then we could also go on to Sirius, the dog star, which is brightest star to us. We see this a lot in the night sky in the northern hemisphere. And Sirius is, let's see, what do we have for Sirius? It's about 8.6 light years away. It's a little further, okay? I mean, it's a little further, but in the light of the entire galaxy, it's pretty close. Now another one, Polaris, or what we know as the North Star here in the northern hemisphere, is a lot further away. That is a distance of 430 light years approximately. Okay. So let's do a example conversion. And there's many we could do. Okay, example conversion would be, let's say I wanted to know Sirius in terms of kilometers. So how far away is it in kilometers if it's 8.6 light years away? Well, what we could do directly is we could say, well, that's 8.6 light years, okay? And I'm going to multiply that by what I know the factor is. So I could say I know that 1 light year is equivalent to 9.46 times 10 to the 12 kilometers. Okay. And if I multiply these numbers, I say 8.6 I get 8.14. These cancel, and I get 8.14, and this is just approximate, times 10 to the 13 kilometers. Wow, you can see why we need light years to reflect larger distances in the cosmos, okay? Other distances that come up with light years, well, polar is 430 light years, but when we talk about, there's many other galaxies, dwarf galaxies that are closer than the Andromeda, which we used to think was the nearest galaxy. But Andromeda galaxy is a huge galaxy and visible. It's one of the furthest objects that's visible with the unaided eye. So Andromeda galaxy and I know this measurement has fluctuated over time as we get more data, is approximately 2 million light years away. Okay, that's mind-boggling. The Milky Way galaxy, our own galaxy, is about 100,000 light years across. The observable universe, that's a mind-boggling notion, but it's the edge of what we could see from the light that has traveled since the Big Bang, the birth of the universe. So, you know, at the beginning of time, we were one blended hot soup of all space and time and all the matter there. So the matter and energy were the same thing, and then boom, everything, all the cosmos were created through the Big Bang, which we have evidence for, and it's been expanding and growing ever since. And the limit of our views, we cannot see the entire universe, we can only see the outer rim of the observable universe, and that's approximately 93 billion light years. Okay, 9.3 times 10 to the 10 light years. Let's double check my numbers. In diameter. Okay, so the radius is half that. So big numbers. And if you wanted to look a little bit more in depth on how you get a light year, I'm going to leave this calculation up there. Maybe you had an internet outage, but you remember the speed of light, but you couldn't remember the conversion factor for a light year being this many kilometers. Okay, what's another way? Alternatively, I won't expect this of you, but it is nice to know how to do this. You could say 8.6 light years. If I wanted to convert this to a value in kilometers, what I would do is figure out light year is based on the distance that light travels at the speed of light. I would look at the speed of light and I'd say, I know that light travels in a vacuum at the speed 3 times 10 to the power 8 meters every second. Okay, and what I want to do next is add up all those seconds and figure out how many meters each of those seconds contribute to that entire light year distance. So I would multiply this by, okay, well, I also know that in 1 second, there's 60 seconds in 1 minute, and I could get a light minute out of that. And I also know that there are 60 minutes in 1 hour, and I get a light hour out of that. And I also know that, well, let's see, we could get a day out of this, right? We could say there's about 24 hours in a day. Now that changes. So that's based on the rotation of the Earth, which is not a physical constant of the universe. So we would say times 24 hours. So I'm approximating here, 24 hours in a day. And now I have a light day. I'm going to have to make a little indentation in board space and time here. Okay, I'm going to have to now approximate how many days there are in a year to get it to a light year. So I know that there are approximately 365.25 days, if we can include the leap year. And I can multiply all that, so excuse my overlap. Rid of that, and this will give me the value that I want. Okay, so that's a really big number, but it can be done. Typically, what you could do is you could verify that this gives you your conversion factor. So if I say 3 times 10 to the 8th, then times 60, then times 60 again, then times 24, then times 365.25, I get a value, I get 9.467 in my case. And then I would multiply by 8.6, and I get 8.14 times 10 to the 16 meters, which we need to reduce by 3 powers of 10 to get kilometers. 8.14 times 10 to the 13 km, and that's how it's done. It really helps. I know this might be a little much or intimidating to you, but it's good to know how that's derived. And one last unit we want to look at is the parsec, which is a little different than the light year. The parsec is based on how we divide up the sky that we see in terms of degrees, in terms of the spherical geometry units we use.
We also use, so light years is one that's used, but we also use this unit called parsec because it relates to angular measures, which we use a lot of in astronomy. We also use the parsec, which we use the symbol PC to represent. Okay. We use the parsec, which can be converted to light years and also relates to the angular measures of the sky. Where, I'm going to continue this, where
1 parsec is equal to, you can use this direct conversion, 3.26 light years. So just as you thought a light year was big, now think of something even bigger, a parsec. Okay. So 1 parsec is 3.26 light years. That's very big. So this is the factor we use. And the parsec is, we'll do angular measures, so it's the distance. Another way of looking at it, it's a distance, I should use complete sentence, the parsec is the distance in which the mean, which is another way of saying your average, the mean average radius of Earth's orbit subtends an angle of 1 arc second. Okay, so arc second, we have to understand what that is. And we'll see that 60 arc seconds make up an arc minute, and 60 arc minutes make up a degree. So if we divide the sky up into 360 degrees surrounding us, which is what we do in astronomy, we can look at 1 degree of space. Now, if you look at the moon, it's about 1/2 a degree in size from where we are. And then if we break that down, that's about 30 arc minutes. So if we break that down some more, we could make it into arc seconds. That would be 30 times 60 arc seconds. And smaller objects, obviously stars are really not that large in the night sky. So we have to use arc minutes and arc seconds to express their size because they're so far away. And we know that distance really impacts the size of the objects we see. So parsecs comes in handy when we relate it to angular measures, which is a topic you do more a little later on in astronomy. But we can practice this number right here. We could do some simple conversions between parsecs and light years. And of course, if we know how many meters a light year is, then we can figure out how many parsecs it is. So why don't we go ahead and do this? Look at Sirius' distance, not in terms of light years, but in terms of parsecs. So how far away is Sirius, the dog star, in parsecs? So let's look at how far away So we know it's 8.6 light years away. Let's look at parsecs. So what we want to do is write down what we have. We have 8.6 light years. And again, sometimes I'll use just LY or LYS. Typically we just say LY. So 8.61 light years times the conversion factor to parsecs. Now, this is really handy. I know what's going to happen is this number, if I know that 1 parsec is 3.26 light years, I know parsec is a bigger measure of distance. So I know this number is going to get smaller. So I'm going to say 3.26 light years here because I want to get rid of my light years and I want to form an answer in parsecs. 1 parsec. So that's my conversion factor right here. And this will give me an answer that will be in parsecs. So let's see how many parsecs this is. So looking at 8.61 divided by 3.26, you get a distance that's just 2.64 parsecs. Nice simple factor. Of course, we could take that and convert it to kilometers as well. We'd want to go to our light year kilometer conversion or a light year meter conversion, and so on. Okay, so the distances get mind-boggling when we're talking about astronomy. And just a last bit here on angular measures. These are ways that we approximate the size of objects in the sky. And I mentioned a little bit, angular measures are approximations relating distance and size. Okay? So what we're going to look at is, we're going to look at what happens when we divide the sky up into 360 degrees. So here we have our surrounding sky. Here's little Earth right here. And if we extend our longitude, our latitude, we create the celestial sphere. And we also extend our equator to become the celestial equator, and our poles become the north and south celestial poles. We'll have this surrounding sphere of stars, which we use for navigation. So we looked at some of that. But this whole circle around there is 360 degrees. Okay. And each of those little sections, so if we're on the Earth and we're like spotting the moon right here, we spot the moon and it looks like it's only about, this is not to scale for sure. So here's the moon. It's approximately half a degree. Okay. Well, for other objects, especially like objects that the Hubble Space Telescope sees and some of the other smaller objects, we start not using degrees, we start using measures of arc minutes and arc seconds. Okay, so what we have to look at is we divide the sky 360 degrees, you divide the surrounding sky. But the degree measures are only appropriate really for big objects like the moon, the sun. Moon and sun are approximately roughly the same size, which gives us the eclipses. If we saw a comet in the sky, we might describe it by the amount of degrees. If you use your pinky, that's about a 1/2 to 1 degree measure. That's a good approximation. So maybe we have 3 pinkies across. We see a comet out there. We could roughly say that's anywhere from 1.5 to 3 degrees. So these are good ways of approximating larger objects. However, we know 1 degree equals 60 minutes, okay, which equals 3,600 seconds. So if you take 1 degree measure, and I'm going to try to make something to scale here. Let's call this 1 degree. 1 degree here. We could break this up into 60 pieces. 10, 20, 30, 40, 50, 60. That's 60 degrees. And if we take this chunk right here, we could break this one further into 60 seconds. Really small objects will be measured in size using arc seconds. All right, that's it for now. Thank you, and keep measuring. Okay, that is a start of some mind-boggling numbers in astronomy. So many of these units you will see over and over again and build on those. So important foundations for astronomy.